Okay. Well, first of all, sincerely, thanks very much to the organizers for inviting me. Of course, it's nice to have a chance to come to Florence, but more seriously than that, I think this series of schools on statistical physics has developed a really high reputation over the years that it's been running. And so I feel it's very much an honor to be invited to speak here. Um, so, what I'm going to talk about, I think, fits in very well together with the things that Sylvia was talking about yesterday. And I'll try to leave out from my introduction most of the things that Sylvia mentioned so that we don't duplicate unnecessarily, although there are a few points which seem to me so central that I should repeat them in my own lecture. So the plan for what I'm going to talk about is, first of all, I'll give an introduction, and then I want to try and take you through three separate calculations, pretty much from the literature, of different phenomena that you can study in random quantum circuits. So the first one will be to do with operator dynamics in the Heisenberg representation. The second one will be to do with entanglement spreading, and then the final part will be to do with spectral correlations in random quantum circuits, which, as you'll see if you don't know already, are simple tractable models for many body quantum systems. And I should say I've almost certainly got far too much material, and I'll be determined to get through it, probably much too fast. And so one of your jobs is to ask me questions and to slow me down. Now I see that Sylvia has produced some extremely nice and very detailed notes. I'm afraid I haven't done that myself, but there is a good review covering this topic, which I've cited in the abstract to my talk, which is available on the website for the school. So that's a review in Annual Reviews of Condensed Matter Physics by Fisher, Kamani, Nahum, and Vijay. And I will be providing some problems, but I haven't done yet. And in the meantime, I encourage you to get started on Sylvia's problems, which in any case are quite relevant to what I'm talking about. So what are we trying to do? Well, the aim in this area is to understand dynamics in generic many-body quantum systems. So some of that deserves some qualification. So when we say generic, what we mean is either a limited number or no conservation laws at all. So a limited number of conservation laws, so we're excluding, well, most trivially, systems of non-interacting particles where the number of particles in each mode would be conserved, but of course we're also conserving beta-ansatz integrable systems. And you might say, how can you have no conservation laws at all? Because in a Hamiltonian system with a time-independent Hamiltonian, you'd at least have the energy conserved. But you'll see that with random quantum circuits, we're really dealing with systems that have time-dependent Hamiltonians. So in the first instance, we've eliminated even energy as a conserved quantity, although I will mention that we can engineer things so that we put back conserved densities if that's what we want to study. And the other point is that we're studying states high in the spectrum. So we want to exclude, for example, an interacting Fermi liquid at low temperatures where we would have a quasi-particle description, and we could think of the long-lived quasi-particles as the basis for a description of the dynamics. So, whoops. So the central question in the dynamics, and this is something which Sylvia already mentioned, but I think needs to be repeated, is that we expect, in some sense, loss of information on the initial state, and then, in a way, repeating the same point but in different language, we expect approach to equilibrium. And then the question is, how can this be compatible with unitary dynamics? And so in some sense, this must be loss in inverted commas, and equilibrium must in some sense be in inverted commas, but the resolution to the apparent paradox is that the initial information is, in a sense, hidden in many degrees of freedom. And the point of studying random quantum circuits is broadly to give us a context in which we can do calculations that probe all of these ideas. Okay, so now I want to go on to talk about these three different aspects in a very brief way so that people in the audience who maybe haven't heard much about operator growth or entanglement spreading have some sense of what I mean. And just to have something to talk about concretely, I want to illustrate the points with a toy model where I take the Hamiltonian to be simply two spins coupled with an exchange interaction, and I'll take these spins to be spin a half to make the toy problem as simple as possible. So, I mean, at that point, you might raise all sorts of objections. For instance, I said I wanted a limited number of conservation laws, and this is just a two-site nearest neighbor Heisenberg chain, and even with many sites, it's Bay-Transat's integrable, but the point is just to have something in mind to illustrate the ideas. So if we think, first of all, about operator growth, then we want to consider some observable. For example, one component of one of these spins, and think about how it evolves in the Heisenberg picture. So we take the operator and we evolve it in time in the usual way. And the basic idea is that we can choose the initial operator to be simple, but generically under time evolution, the operator becomes complicated. And in the toy example, I could take the operator, say, to be the Z component of the first of the two spins, and then for short times, I can expand the exponentials, and so I would say that O of t is the original operator plus it times the commutator plus of order t squared, and then if I work this out for the toy example, the commutator gives me terms like that. So the point is that this is simple in the sense that it involves an operator acting only on one site, and this is more complicated because it involves operators acting at two sites. And then if we go on and think about entanglement growth, then really we're switching to the Schrödinger picture, and we think of a state evolving in time from some initial state, and we might choose the initial state to be one with low entanglement, and generically we'll go to something with high entanglement. And in the toy example, I could take the wave function at time 0 to be a product state in the site basis, say with the spin on the first site up and the spin on the second side down. And then what you find, since you can obviously easily find the eigenvalues and eigenvectors of that Hamiltonian, is something which is basically up to a phase, a superposition of the original state and a state with the spins both flipped, and then at a general time, because you've got a superposition of these two states, you've got entanglement that wasn't present in the initial state. So this is entangled for times jt that are not multiples of pi. So if that statement seems unfamiliar to you, of course you can easily follow through the calculation. Any questions about any of the points that I was making there? Yes. Yeah, absolutely. And this is just trying to illustrate the beginnings of the idea. And when we go on to do serious calculations on random quantum circuits, then certainly we'll think about arbitrarily large times. Yeah. Any other points? Yes. Yeah, so it's useful to discuss both large finite systems explicitly and to understand what happens if you take the thermodynamic limit. But I would say there's a lot of value in this area in understanding large finite systems without taking the thermodynamic limit too early on. Yes. I'm sorry, I didn't. Yeah. I don't think I can give a solid answer to that, but I think with a large system with couplings between all the parts, then generically, yeah. All right. I think if I try to give a general answer, it'll turn out that there's some obvious counterexample fairly quickly. Was there another question? Okay. So there was just one more point which I wanted to make by way of illustrating these ideas, and it's to do with the final section of the lectures, which is on level correlations. And again, I wanted to illustrate the point with a very simple example. So this idea of level repulsion, which we heard something on yesterday, it's a signature of generic Hamiltonians generic in the sense that I was explaining. And if you consider a general Hermitian 2x2 matrix, then you can write it as some real constant times the unit matrix plus a vector of 3 real components dotted into a vector of Pauli's. So this is the vector with Pauli matrices as its components, and this is a 3-component real vector. And then the eigenvalue splitting so the eigenvalues A0 plus or minus the modulus of this vector A, so the eigenvalue separation or the eigenvalues are A0 plus or minus the modulus of this vector A. And so to have degeneracy requires, well, if A is a 3-component vector, it requires tuning 3 real variables. To 0, and so degeneracies are non-generic. Okay, so all those 3 things, the fact that operators grow under time evolution, the fact that entanglement spreads, and the fact that degeneracies are non-generic, those were all understood, at least qualitatively, in the early days of quantum mechanics in the 1930s. So you might ask, what are we doing 90 years later, still talking about it? And the point of random unitary circuits is that they give us a way of doing quantitative calculations on these phenomena. And in particular, they give us a way of studying the consequences of having a system with local interactions and spatial structure. Okay, so to talk about random unitary circuits, the first thing that I need to do is say a little bit about random matrix theory. And fortunately, Silvia said a lot of what does need to be said yesterday, but I'd like to mention a few different aspects, partly to do with the historical perspective, not for the sake of history, but because I think the way of thinking is good to bear in mind. And so when random matrix theory, at least in the context of quantum systems, was being developed, the question the physicists faced in the context of nuclear physics in the 1950s and 1960s was the one I'm talking about, how to calculate properties of generic systems and the basic answer is that for any individual system, well, firstly, from an analytical point of view, it's impossible. Although, of course, numerically, if the system size is not too big, we can do it. But you can also argue that anyway, it's undesirable. So perhaps it sounds like sour grapes to say that having realized that something's impossible, you don't want to do it anyway. But the point is that, at least in the nuclear physics context where these ideas were developed, and the problem was to understand experiments that were measuring the energies of highly excited resonances in nuclei, there's no hope of having a model for the nucleon-nucleon interactions that would be good enough to understand the precise values of individual resonances in a specific system. And so what you want is a whole different way of thinking. And this is one of the things that I want to emphasize from random matrix theory. And there's a phrase that I think is more or less due to Dyson, which is that because it's impossible and undesirable to calculate properties of an individual system, what we should do instead is renounce all knowledge of the Hamiltonian and instead we think, in the way that Silvia explained, about an ensemble of Hamiltonians, and instead of calculating the properties of individual systems, we calculate ensemble averages of properties of the systems. And we go, it turns out, from having a problem that would be impossible to having a problem when we think about these ensemble averages, which is not only possible, but actually, at least given all of the machinery that's been developed up till now, is not too difficult. And of course, in the process, you want to understand how much the property that you're thinking about fluctuates between different members of the ensemble and so on. But those are all issues which you can look at when you come to the particular problem. So that brings us to the question of ensembles. And we had a more detailed discussion of that question in yesterday's lecture. So let me just recap the simplest point. So if we take H to be an n by n complex Hermitian matrix, to represent the Hamiltonian, then we can take the probability distribution to be proportional, that's up to a normalization constant, to a Gaussian, and Sylvia left some constants open, but I'll make a definite choice here, e to the minus n times the trace of h squared. And of course, when you write a probability distribution for the Hamiltonian, implicitly you have in mind choosing some coordinates, and we're taking the coordinates here to be the real and imaginary parts of the individual off-diagonal matrix elements and the real parts of the diagonal matrix elements. And so that volume element I'm leaving out of what I've written. And this ensemble, which is the GUE, the Gaussian unitary ensemble, is particularly simple because actually the individual matrix elements are independently Gaussian distributed, apart from the constraint that's imposed from the fact that the matrix is Hermitian, so that elements across the diagonal are related by complex conjugation. So it's particularly simple because the matrix elements are statistically independent, and then also, even more important, by design, the probability density is invariant under unitary rotations of the matrix because, of course, the trace of the square of the Hamiltonian is invariant under unitary rotations. So any questions on things that I've said up to this point? Yes? Yeah, okay, thanks. There are certainly points all along where I'm sliding over details, and I'm very happy to fill in if anyone asks about them. So more explicitly, I think what you're asking is that I could write this as something like that, and you're saying, what do I mean by this dH? So what I mean is that dH, well, it's got to involve as coordinates all the elements of the Hamiltonian. So first of all, the diagonal elements are real. So I have a product from k to 1 to n of dh kk, and then I have the off-diagonal elements, and I'll just take the upper triangle because the lower triangle is related by complex conjugation, and then I can have as coordinates the real part of hij and the imaginary part of hij. So this is a volume element, and then in terms of these same coordinates, I can write the trace of h squared, and it's straightforward. Is that enough detail to make things clear? Great. Thanks for that question, and I encourage other people to ask similar questions. Okay. So I've talked about the Gaussian unitary ensemble, the Gaussian unitary ensemble, and this is something that we can use to represent, Hamiltonians, or more generally, something that we can use in problems where we want to talk about Hermitian matrices that we take to be random. But we're thinking about dynamics, and if we think about time evolution, then obviously in quantum mechanics that's generated by, it's described by a unitary matrix, and so we also want to be able to think about ensembles of unitary matrices, and the one that I'll need to refer to a lot is the circular unitary ensemble. So now one point is that if we're thinking about Hermitian matrices, because the elements are unbounded, we have an unbounded space, and we have to have either this Gaussian or some other function in there to have a probability density that we can normalize. But for unitary matrices, the manifold is compact, and so we can simply take a uniform distribution over the group. And this is known as the Haar measure. And it's not so convenient to introduce explicit coordinates in the way that I sketched in the case of the GUE because of the curvature of the group, but you can say that you have a measure over these unitary matrices. So I'll take these to be n by n unitary matrices, and the fact that the distribution is uniform, you can summarize by saying that this measure is invariant under either left multiplication, actually I'll use the letter V, or right multiplication, where V is a unitary fixed matrix. So this is some analog of translation invariance for the unitary group. Okay, so maybe the next point to make is, having advertised some of these beautiful ideas from the 1950s and 60s involving random matrix theory, what are the strengths and limitations? So, what's the scope of random matrix theory? Well, as we heard a little bit yesterday, and as you can develop in more detail, it accounts for correlations between eigenvalues. So I made the elementary point that generically you don't have degeneracies, but going beyond that, you have rather specific correlations in the distribution of eigenvalues. So it accounts for so there are some limitations to the range of applicability of random matrix theory, which I hope to talk about in my final lecture. But at least there's typically a broad window in which random matrix theory does apply for a particular system, and you can actually use it, as was mentioned yesterday, as a diagnostic of what you might call quantum chaotic behavior. But on the other hand, a lot of the time we're also interested in the eigenvectors, and from that point of view, random matrix theory doesn't do so much for you because the ensembles that you write down, or at least the simplest one, the Gaussian unitary ensemble, generates isotropically distributed and so that maybe is a kind of null statement which you want to compare any physical system against, but there's obviously not much scope for interesting behavior. And then when you think of the limitations, of random matrix theory, well, there are all the limitations that are implied by having an isotropic distribution of eigenvectors, but in terms of the description of the system, the main point is that all elements of the Hamiltonian are generically non-zero if you choose any specific basis and then think about the ensemble of random matrices. And clearly that's not quite right if you're trying to model a physical system. At least with most physical systems, we'd think about defining a Fock space, say, in the number state basis, and then we'd write down some Hamiltonian, which would probably involve few body operators acting on these basis states, And then you'd find that most matrix elements of that Hamiltonian would be zero because you'd only have non-zero matrix elements between states whose occupation numbers differ in only a small number of orbitals. So the point of random unitary circuits is to give us an example of a system where in particular we get around this feature of random matrix theory and we have some notion of locality and with that locality and also few body interactions, and so that most matrix elements of the evolution operator would be zero, and only small numbers of the matrix elements are non-zero. So that's most of what I want to say by introduction, except for defining random unitary circuits, which I'll do in a moment. I think there's time before the break. But are there any questions on things I said up to now? Yes. So yeah, we're sort of generic enough. In a way, we're too generic. The natural thing with random unitary circuits is to write them in a qubit or qubit or spin language. And so the restrictions on matrix elements that would come from the Pauli exclusion principle are not so naturally built in. So yeah, I mean there are some roots around that, but it's a reasonable point to make that we're thinking in the first instance in terms of spin systems or generalizations rather than systems where the Pauli exclusion principle is at the heart of things. Yes. Okay. Well, one example in which it shows up is precisely when you think about these ways of characterizing dynamics. So when you think about operator spreading or when you think about entanglement spreading. So immediately after the break, I'll start talking about operator spreading. And the basic point is that when you go beyond the two-site system, as the operators get more and more complicated, it's not just that terms appear absolutely anywhere all at once. What happens is that the operators gradually get more and more complicated in a way that reflects the geometry of the system if you have local interactions. And it's that would be different if you modeled the Hamiltonian by a random matrix with all of the elements non-zero. One thing I did mean to say is that, of course, you can try to do away with this limitation of having all the matrix elements non-zero without necessarily including spatial structure. So, for example, the SYK model has few body interactions, but no spatial structure. But in some ways, the most, in quotes, realistic versions of a problem have both a restriction to few body interactions and spatial structure. Okay, so now what do I mean by random unitary circuits? So in terms of philosophy, these minimally structured models for quantum dynamics and really one of the central insights is that, well, of course, in dynamics, a lot of the time we're talking about time evolution, and it's easier to model the evolution operator directly instead of the Hamiltonian. Now, I mean, clearly you can write down a reasonable model for the Hamiltonian and then think about e to the minus IHT and try to use the machinery of random matrix theory. But it just turns out, and this was an insight, that it's more convenient if we start with the problem of modeling the evolution operator. And so, of course, we need to specify the system that we're thinking about. And so I'm going to need to draw pictures, and there'll be pictures in space-time. And since the board is two-dimensional, if time takes up one dimension, I need the other dimension to be space. So we'll think about a chain, but higher dimensions are also okay of sites, and at each site we'll have either a qubit, or if we want something with a higher Hilbert space dimension, a qubit, or we might call it, from a condensed matter perspective, a spin. But anyway, the point is that we have q-dimensional local Hilbert space, and then from these local Hilbert spaces, we make a Fock space as a tensor product. And so if we have an L-site system, that gives us a q to the power L dimensional Fock space. And then, as I said, we want to model time evolution. And first of all, I'll draw a picture, and then I'll fill in a bit of what one says to explain what it means. So time in one direction and space in the other direction, and then world lines, if you want to be fancy, of the different sites in the system. And then as time goes by, we think of gates in the quantum information terminology that act on, for example, pairs of sites and entangle them. So you might have something like this to represent the time evolution operator. And I'll use W with the time interval as an argument to denote that. And so then we need to expand a bit on the notation. So this gate, it describes time evolution and it couples a pair of sites. And so if each of the sites has a q-dimensional Hilbert space, then together the pair has a q-squared dimensional Hilbert space. And because this represents time evolution in quantum mechanics, it corresponds to a unitary matrix. So this is a q squared by q squared unitary matrix. And then we need to fill in some details. So at the moment, I've just been drawing lines for the sites, for the world lines of the sites, but the sites can be in different states, and we can label these legs with letters corresponding to the different states. So this will represent an element of this unitary matrix, and the element will be labeled according to these letters. And of course, it's because we're taking this q-squared dimensional space to be a tensor product that we've got double letters as the labels. So in a more conventional labeling, we might write things like this, where beta runs from 1 to q, beta runs from 1 to q squared, and it stands for that pair CD, and this stands for the pair AB. And so if you take the whole network, then we can put labels on A1, A2, up to AL, and B1, B2, up to BL. And so we have a matrix W of T with labels A1, A2, AL, and B1, BL. So these are beta and alpha. And if we think of attaching labels to all of the internal lines in the picture, then we're defining a particular Feynman path through the many-body space. And if we sum over the labels on all of the individual lines in the interior, then we're summing over different Feynman paths. And each Feynman path contributes an amplitude to this overall amplitude to propagate from alpha to beta. And those amplitudes are got by multiplying together the elements of the individual unitaries for the different gates in the system. Okay, any quick questions before I break? Yes, I'm sorry. Yeah, you're right. So yes, I should switch the A's and the B's here. Thank you. Yeah. Yes. Yes. Okay. Well, I guess you're making the point that I haven't quite explained how these random matrix ideas tie in with what I'm saying about random unitary circuits, and of course that's true. So what I omitted to say, which is the one of the crucial points, but it'll be amplified in what comes later, is that if we take these unitaries to be from the circular unitary ensemble, then it turns out we can calculate some properties of these systems analytically. Yes. No, that's absolutely true. I've got some more points that I need to make about introducing and defining random unitary circuits, but I realize that I'm a bit late for the break. Yes. Yeah, that's another point which I want to elaborate on, but I'll wait till after the break. Thanks. But the basic answer is no. We can have three-site interactions if we like. Okay, I think I've gone on long enough. I'd better pause there. Thank you. Okay, hello again, everyone. So I want to continue directly in the direction I was going before the break. So of course I talked about this idea of quantum circuits, and in one of the questions at the end, someone pointed out that I'd failed to mention the key point, which is that average quantities are tractable. We can compute them if these gates are chosen randomly. And that means in practice that we'll take them from the hard distribution. So then there are a few more things to say, and I guess next most important one is that if we try to relate this back to a Hamiltonian description of the quantum mechanics, then it's pretty obvious that although we must be able to read off a Hamiltonian from this time-dependent unitary, it'll have to be a Hamiltonian that varies as a function of time. I mean, I've drawn things really in terms of time steps, and at different time steps, I have different pairs of sites coupled by the gate. So a random unitary circuit is equivalent to a Hamiltonian that's a function of time. Now, I guess another point which it's important to make is that I've drawn here a particular example of a random unitary circuit to have something explicit, but I made a lot of choices. So, in point of fact, this particular structure has come to be known in the field as a brickwork circuit. And there are different ways of constructing circuits. So we have some variants with different architecture or different geometry. So, for instance, as well as choosing the gates from an ensemble such as the circular unitary ensemble, you could actually put the gates in random locations. So you could take the gates to couple randomly chosen nearest neighbor pairs of sites, so that as time goes by, we select a nearest neighbor pair and draw a gate to act on that pair, and then in the next time step we take a different randomly chosen nearest neighbor pair, and so on. Another possibility is that we can have gates that couple more than two sites. So if we couple three neighboring sites, then clearly we need a unitary which has dimension q cubed by q cubed, and so on. But that doesn't really change the idea. Something more significant is to try to model a system with a conservation law. So the fact that we have a time-dependent Hamiltonian here means that in contrast to systems with time-independent Hamiltonians, we no longer have energy as a conserved quantity. So in fact, we have in the most basic version of a random unitary circuit, we have no conservation laws at all. And although a few years ago I thought of Floquet systems as I thought of systems with time-dependent Hamiltonians as being rather peculiar. exceptions to the general class of problems, I've now come to feel that having no conservation laws at all is the kind of purest and most simple example of a generic system, and putting conservation laws back is something that you might choose to do when you've studied the most basic problem reasonably thoroughly. But if you do want to put a conservation law back, then you can go from a system with a q-dimensional Hilbert space to something with basically spin half times a q-dimensional Hilbert space. So in other words, at each site you have 2q dimensions, and then a two-site gate. Well, we have a unitary of size 2q all squared, and we can divide that into blocks, and we can have the spin a half degrees of freedom, for instance, both up in the initial and final states, or one up and one down, or both down. And if we had no conserved quantities, then this 2q all squared unitary would have non-zero elements everywhere. But if we want to conserve spin, then we have non-zero elements only in these blocks, and we put zeros elsewhere. And then, in the spirit of the things that I was saying earlier, we can take each of these blocks to be independent, hard distributed unitaries. And then the final variant, which I want to talk about because it'll be important in my final lecture, is to think about systems with a time dependence which is periodic. That's to say, to think about Floquet systems. So, in general, in Floquet systems, you have a time-dependent Hamiltonian with some period, but I'll take the period to be unity here. And in terms of the pictures that I was drawing previously, then I'll take something like this, or possibly a different geometry, to be an evolution operator for one time step, and I'll take for many time steps I'll take w to the power t. But I find this notation a bit confusing because often you use t to mean transpose. So I prefer to write this with t as an explicit argument. But I'm evolving over a discrete number of time steps, so this t here will always be an integer. And what this means practically in terms of the circuit is that each time I have a gate that acts between, say, the first and second sites, then in a Floquet system, although I will choose the gate at random the first time I act, at later time steps, when I'm acting on the same pair of sites, I'll use the same realization of a random unitary, which is quite different from what I have in mind in the simplest version of a random unitary circuit, where at each successive time step, I choose a gate in a way that's uncorrelated with the previous choices that I made. Yes. Well, you could do it either way, but the way I was trying to represent things here, it was an extra degree of freedom. So I'm stepping up from a Q-dimensional Hilbert space at each site to a Hilbert space of dimension 2Q. It's a physical degree of freedom. Yeah. Yes. Yes. I mean, that was how I talked about a Haar measure. Yes. I'm sorry, I'm not hearing you well. Um, I think all of those questions go away when we calculate average quantities. So if you're uh, studying a specific realization, then yes, you could think about the gauge and whether you were going to use the same gauge at different time steps and so on. But really, once you average over different choices of the gate, especially if the average is with the Haar measure, I think all those issues go away. Um, any other questions? Yes. Um, so I'm hesitating because there are two ways of looking at it, but let me stick with the way that I was presenting things, where the idea is that you take a spinor half uh, degree of freedom, which is a new degree of freedom, and you take the original Q-dimensional local Hilbert space, and then we just make sure that SZ is conserved. And so if two sites, you have an initial state in which both spins are up, and the other degrees of freedom are in whatever state they are, then you want to evolve only to a final state with both spins up. And then less trivially, if one spin at the pair of sites is up and the other is down, then you can evolve to a final state where, again, on the pair of sites, one spin is up and the other is down. Uh, It's a physical degree of freedom which gets entangled with the other degrees of freedom here. I mean, the reason I was hesitating, as I said, is because there are two ways you can present it. And the simplest thing actually is just to have the spinor half, and then this matrix here would be 2 by 2, and these would be 1 by 1. Okay, so there are all these variants and the possibility of studying Floquet systems I hope to come to in the final lecture, but for now I'll focus on the choices that I started out with originally. That's to say this brickwork architecture and unitaries, which I'll choose independently at each time step with a hard distribution. And what I want to go on to, so that was the end of the introduction, I want to go on to the first of these three ways of characterizing dynamics. That's to say, in terms of operator growth. And first of all, I want to make some general points, and then I want to work towards an explicit calculation using these ideas of random quantum circuits. So the overall section is operator dynamics. And the first point is something that's much older than the study of random quantum circuits, known as the Lieb-Robinson bound. And the idea here is that you think, in fact, originally it was for Hamiltonian systems, but we think about a lattice model with a finite local Hilbert space dimension and local interactions. And I'll use the notation curly O for an operator with a label Y to mean an operator that acts at site Y. And then we want to think about time evolution. So we can think of time evolution of an operator that initially just acts at a site X. And one way to probe how this evolves is to think about the commutator of that operator with a site with the operator that acts somewhere else. And what we'd like to think about is how big that commutator is in terms, for instance, of the operator norm. And what Lieb and Robinson showed is something quite remarkable. And basically, it's along the lines of what you would expect in a Lorentz invariant system. So in a Lorentz invariant system, you'd say that information, of course, can't travel faster than the speed of light, so that you would have a light cone extending from the place where this operator acts, and the commutator must be zero if y lies outside the light cone of the operator at x. Now, we're thinking about lattice systems, no hint of relativity, but the picture is that in terms of space and time, if we have points x and y, then in terms of the behavior of the operator, there's some light cone and the commutator is small outside the light cone. Now, of course, there's no speed of light in this problem. Instead, we just have interactions in whatever the Hamiltonian is. And the point is that those interactions and h bar and the lattice spacing define an effective velocity, and the result is that you can get some upper bound on this commutator, which has the form the distance between the sites minus a velocity times time, and this velocity, which we talk about now as the butterfly velocity, is determined by the interactions. So if you think about the form of this bound, if time is small and the separation between x and y is large, then the exponential is small, and we're out here somewhere, and so the commutator is small. But on the other hand, if we're inside the light cone, then the argument of these brackets, t is large, is negative, and I guess actually it should be modulus t. The argument inside these brackets is negative, the exponential is large, and the bound doesn't really tell you anything at all. Yes? Well, I guess one answer to that is that by doing the calculation that I'm going to sketch in, well, either later this lecture or the beginning of the next lecture, you'll get some intuition. But the basic point is going to be that operators grow from the ends. Operators expand as time goes by, and they grow at a steady rate from the ends, as you'll see in more detail. But that's in the context of random unitary circuits, and so I'd say one of the nice things about random unitary circuits is that they give you an explicit insight into this process. Okay. So that's a beautiful result, which was proved rigorously in the 1970s as something that applies to these systems with local interactions rather generally. But even so, you might like explicit calculations, and you might like results that are not simply upper bounds, but actual results for specific systems. And that's what I'm going to describe. But before describing that, it's worth introducing a bit more background. And the other piece of background is to introduce what's called the out-of-time order correlator. And the first point is that the Lieb-Robinson result involves the operator norm of the commutator, which in a sense is the gold-plated quantity. If you know that, you have bounds on other things. But from the point of view of concrete calculations, rather than rigorous proofs, it's not such a convenient thing to deal with. And what we'd like to do instead is have some quantity that, for example, we can begin to discuss in the language of quantum circuits, and in particular, since the key idea behind quantum circuits, random quantum circuits, is that we're going to do ensemble averages, we want something that we can ensemble average. So if you take the commutator itself, you definitely don't want to ensemble average that, because there are two ways that the ensemble average could be zero. It could be that every instance of the system gives you a commutator that's zero, or it might be that different instances of the system give you non-zero commutators, but sometimes with one sign or one phase, and in other instances with a different sign or phase, and so that the ensemble average is zero for that reason. So what we want to do instead is take the square of the commutator. So we avoid the operator norm and consider the commutator times, of course, the commutator is anti-Hermitian, and so to have something that's positive definite, I want to multiply it by its Hermitian conjugate, and I'll just represent that by writing modulus squared, but it's a slightly sloppy notation, and then I want to think about the ensemble average. And this I'll call a correlator, which depends on X and Y, but if I have an ensemble which is translation invariant, then it'll depend on the difference between X and Y and on time. And this average, I should specify, so on the one hand, it's an ensemble average. But before that, we need to think for any particular example of the system of some kind of average over initial states, or and so we might think about a thermal average. And a thermal average, of course, would be the trace with, in a Hamiltonian system, e to the minus beta h times the thing that we're averaging, normalized with the partition function. But for a random unitary circuit, well, firstly, we don't have a Hamiltonian, we have a time-dependent Hamiltonian, and then secondly, with systems where the Hamiltonian is time-dependent, you naturally pump energy into the system, and so the long time state would be an infinite temperature state, and so that would mean that the natural value of beta, the inverse temperature, would be zero. So this would go over when we take beta to be zero, just to be a trace of the quantity that we're averaging, normalized with the Hilbert space dimension, which is Q to the L. Okay, so the idea is these angular brackets are standing for both types of average. And if we think about the behavior of C of x minus y and t and expand this commutator times its Hermitian conjugate, then, well, from this normalization, we have a prefactor of q to the minus L, and then from this definition of the average, we have a trace, and then we still have the ensemble average. And if you think about multiplying this commutator by its Hermitian conjugate, then obviously each commutator has two terms in it, so altogether you get four terms, and it turns out that they come in pairs, and we can account for that by putting a 2 out the front and writing the two contributions. So one of the contributions is a simple one where we have OX of t squared times OY at time 0. And the other kind, which comes with the opposite sign from the commutator, is where we have the operators in what's called out of time order. So we have O of y, OX of t, O of y, OX of t. So if you compare that with the kind of correlators that you normally discuss in statistical physics, typically as you go, say, from right to left, the time argument of the operators would increase as you go from one to the next. But here we go from time 0 to time t, back to time 0, and then to time t. And so that's the bit of the correlator that's out of time order. And if we discuss the behavior that we might expect, then at early times, if the points x and y are far apart from each other, then according to the Lieb-Robinson ideas, the operators should commute. And if they commute, then this correlator is small. But on the other hand, at later times, one operator has grown so that it overlaps with the other one, and then they no longer commute, and so you get a step between two types of behavior, and the time when this step appears depends on the separation and this butterfly velocity. Yes. No, I don't think ergodicity comes into this. I mean, um, yeah, I mean, we don't need to make some equivalence between an ensemble average and the thermal average. And most of this, I think you could apply perfectly well to a specific example. And it would be natural to take the infinite temperature average as the average, quantum average, and then you needn't do the ensemble average, but you'd have some behavior like this, but I guess you'd have fluctuations as a function of time, which you'd only remove by going to an ensemble average. Yes. So, so for a specific realization of the quantum system, taking the trace and normalizing it in this way is the infinite temperature average. But if the overall program is to build on the ideas of random matrix theory and compute properties of an ensemble of systems, then I will still want to average over different choices of the gates. And that's what these angle brackets mean. And unless I do that, it turns out I don't have a chance of carrying out the calculation except numerically. Okay, I guess it would be reasonable to stop there because the next points that I want to make lead into a calculation which I definitely want to present, but maybe it's best doing it in the lecture that I give next.